Welcome back to Very Ordinary Differential Equations. In this lecture, we learn how to take the Laplace transform of higher order equations. Remember that we've already learned how to take the Laplace transform of the derivative of a function. Specifically, when the Laplace transform of little f is given by capital F, we showed that the Laplace transform of little f prime is s capital F of s minus little f of 0. And then we used that result to compute the Laplace transform of a second derivative. Specifically, we just took the second derivative of f and treated it like the first derivative of the first derivative. So, having the derivative of f prime here, we simply put the Laplace transform of f prime there, minus f prime of 0. Then we know how to take the Laplace transform of f prime. It's s f of s minus little f of 0. And we distributed this to get s squared capital F of s minus s little f of 0 minus little f prime of 0. And we did this to take the Laplace transform of second-order differential equations. It doesn't take a whole lot of work to establish an inductive procedure to take the Laplace transform of a higher-order derivative. Specifically, the Laplace transform of the nth derivative of little f is given by s to the n times capital F of s minus a whole bunch of terms. Now, what we are adding up here, we count up which derivative we're taking while we count down the exponent on s. In this formulation, I equals 0 gives us the 0th derivative of little f, which we interpret to mean the original function f. The proof by induction really is not very difficult, but we're not so focused on proving things in these lectures, so we're just going to jump right into using such formulas. So here is the formula for taking the Laplace transform of higher order derivatives of little f. Now we've already remarked that we are counting up which derivative we are taking, while correspondingly counting down what power of s we're multiplying by. In particular, let's see how this formula plays out. When n equals 1, and I'm taking the first derivative here, we have s to the first, capital F, there it is. Then I subtract I going from 0 to 0, so the only term I have to put in is I equals 0. S to the 1 minus 0, or s to the 0, the 0th derivative of f, which we've already remarked is the original function. What if n equals 2? We get s squared, capital F of s, minus, and now we subtract a bunch of terms. We count up which derivative we're taking, so we have the 0th derivative and then the first, the 0th derivative, or the original function, and then the first, while correspondingly multiplying by a decreasing sequence of powers of s. Now when I is 0, this starts off as s to the n minus 1. So in this formula, because we started with the second derivative, we begin with s to the first. Then we decrease that to s to the 0, and then we're done. For the third derivative, our initial term is s cubed capital F. Then we begin subtracting higher powers of s. So from cubed, we go to squared, to first, to 0. And then we start off with little f of 0, and we start counting up derivatives, f prime, f double prime. And once you've reached a term where there are no s's remaining, s to the 0, that's when you are done. So specifically, again, the fourth derivative, we start off with s to the fourth, capital F. Then the rest of the terms are being subtracted. We count down powers of s until we reach a constant. We start off with f of 0, and we start counting up derivatives. Now, can we apply the Laplace transform to differential equations with non-constant coefficients? So we've seen plenty of differential equations where the coefficients were not constants. For example, we could have something like t f prime of t, and then we want to take a Laplace transform of that. Now, there are formulas for computing some things like this. Notably, we can take the Laplace transform of t to the n times a function. This can be computed as a derivative of a Laplace transform. It's actually an integration by parts kind of formula. So the Laplace transform of t to the n times f is negative 1 to the n times the nth derivative of the Laplace transform of little f. There's also results for when this power here is not positive. So the Laplace transform of 1 over t times f. And specifically up here, we didn't just have t times f, but we had t times f prime. So this would be the antiderivative of f, and there are Laplace transform formulas for computing such things. There's also the shifting theorem. This allows us to take the Laplace transform of an exponential times a function. However, in practice, in an introductory course, it's relatively uncommon to be asked to take the Laplace transform of a linear differential equation with non-constant coefficients. So we are going to be restricting ourselves to constant coefficients. It's just worth pointing out that it can be done for non-constant coefficients, but it is a lot of work. So for our first example, let's solve the initial value problem. Y triple prime plus 3y double prime minus y prime minus 3y equals e to the 4t, where our initial values are that y of 0, y prime of 0, and y double prime of 0 are all 0. Now we can solve this problem using the method of undetermined coefficients, and it's not that big of a deal. However, we're not going to. We're going to take the Laplace transform of both sides, so we start off on the left. The Laplace transform of y triple prime is as follows. We start off with s cubed Laplace transform of y, then we subtract a bunch of terms, starting with the next lowest power of s. So from s cubed, we go to s squared times y, s times y prime, constant times y double prime, and now we're done. Because y of 0, y prime of 0, and y double prime of 0 were all given as initial values to be 0, this simplifies very much to just s cubed times the Laplace transform of y. Similarly, here's the Laplace transform of y double prime, which thanks to our initial conditions is just s squared times L of y. Here's the Laplace transform of y prime, which thanks to our initial conditions is just s times the Laplace transform of y. And therefore, the Laplace transform of the entire left side gives us an s cubed 3s squared minus s, and from this term right here, we will just get minus 3 times the Laplace transform of y. So notice that when the initial conditions are all zeros here, the Laplace transform of a differential equation with constant coefficients works out to just be the characteristic polynomial in s times the Laplace transform of y. This characteristic polynomial factors quite nicely as s minus 3, s plus 1, s minus 1. On the right-hand side, we also take a Laplace transform, but it's a lot easier. The Laplace transform of e to the 4t is just 1 over s minus 4. So, setting the left equal to the right, we have s minus 3, s plus 1, s minus 1 times the Laplace transform of y is 1 over s minus 4. Dividing by s minus 3, s plus 1, s minus 1, the Laplace transform of y is just this rational function right here. So we've determined the Laplace transform of y, which solves this initial value problem, must be this rational function right there. We apply partial fraction decomposition as we've grown accustomed to doing when using the Laplace transform, and it works out to this. Okay? It takes some work. I just used a computer algebra system, to be honest. Thankfully, these are all easy to invert. The inverse Laplace transform of 1 over s minus a, remember, is e to the at. So y must be 1/15th e to the 4t minus an 8th e to the 3t plus 1/12th e to the t minus 1/40th e to the minus t. For a second example, let's solve another initial value problem. The fourth derivative of y is e to the 2x sine of 3x plus 1, where our initial values are y of 0 is 1, y prime of 0 is 0, y double prime of 0 is minus 1, and y triple prime of 0 is 0. So we take the Laplace transform of the left, and we just have the Laplace transform of the fourth derivative is s to the fourth times the Laplace transform of y. Then we start subtracting s cubed y of 0, s squared y prime, s y double prime, y triple prime, and then we're out. Thanks to our initial conditions, this is just s to the fourth Laplace transform of y minus s cubed plus s. And on the right-hand side, we take the Laplace transform of e to the 2x sine 3x plus 1. Referring to a table of Laplace transforms, we get 3 over s minus 2 squared plus 3 squared plus 1 over s. Setting the left equal to the right, we end up with this right here. Now we just have to solve for the Laplace transform of y. So if we solve for the Laplace transform of y, we end up with this there. A bunch of rational functions added and subtracted together. We've managed to solve for the Laplace transform as this mess. And again, we have to apply partial fraction decomposition. Doing this by hand would be quite a mess, but I used a computer algebra system. There it is. The Laplace transform of y is 1 over s to the fifth plus 3 over 13 s to the fourth minus 157 over 169 s cubed plus 9 over 2197 s squared plus 28,441 over 28,561 s plus 3 times 199 over 28,561 times the quantity s minus 2 squared plus 3 squared. Which is a mouthful, but we can take the inverse Laplace transform of every term. And there it is, our solution to the differential equation. For our third example, let's solve this initial value problem. We're not doing anything new. We're going to take the Laplace transform of both sides, solve for the Laplace transform of y, apply partial fraction decomposition, and take inverse Laplace transforms of everything. So here's the Laplace transform of the fourth derivative. Now we substitute in our initial values. Y of 0 is 1, y prime of 0 is 2, y double prime of 0 is minus 3, and y triple prime of 0 is 0, and we'll end up with that. Similarly, if I compute the Laplace transform of the third derivative and plug in our initial values, it will simplify as such. Here's the Laplace transform of y double prime and the Laplace transform of y prime. So now what we have to do is take all of these things we've computed and plug them into the original differential equation once we take the Laplace transform of the entire left-hand side. So altogether, here's what we computed as the Laplace transform of the fourth derivative, the third derivative, the second derivative, and the first derivative. Now what we're going to do is take the Laplace transform of the original differential equation. The way I like to do this is now run through term by term, referring to what we've already computed, and just remembering to distribute these constants of 5, 2, 20, and minus 24. But since we already know that the next step is to solve for the Laplace transform of y, I'm going to take these terms first. So what are the terms that get a Laplace transform of y? Here, I'm just going to get s to the fourth times the Laplace transform of y, minus 5s cubed plus 2s squared plus 20s minus 24 of them. So we're going to get all of that times the Laplace transform of y. Now I'm going to take care of all of the terms that don't have the Laplace transform of y. So I get all of these terms here, minus s cubed minus 2s squared plus 3s. Then I have to multiply all of these by minus 5. So plus 5s squared plus 10s minus 15. Multiply these terms by 2, so we get minus 2s minus 4. Multiply this by 20, so we get a minus 20, and then a minus 24, which simplifies to minus s cubed plus 3s squared plus 11s minus 39. So here's the Laplace transform of the left side of the equation we began with. So we've been able to express the Laplace transform of the left side of our differential equation as a polynomial times the Laplace transform of y plus another polynomial. Now, from experience, we know that we're going to need to factor the polynomial which is multiplying the Laplace transform of y, so we may as well do it now. You can use whatever method you like. For example, a computer algebra system if it's allowed in your course. Otherwise, for this particular polynomial, the rational roots theorem will be very productive. But however you do it, here's how that polynomial factors: s minus 2 squared, s minus 3, s plus 2. So now that we've taken the Laplace transform of the entire left-hand side and simplified it as much as we can at this point, we're going to go ahead and turn our attention to the right-hand side. The Laplace transform of the forcing function, 3e to the minus 2t plus e to the t, is given by 3 over s plus 2 plus 1 over s minus 1. Altogether, the Laplace transform of the left-hand side is equal to the Laplace transform of the right-hand side. Having set the Laplace transform of the left equal to the Laplace transform of the right, well, now we divide out by that already factored polynomial. So here is the Laplace transform of y. Now what comes next in our general technique is partial fraction decomposition. And I am definitely going to be using a computer algebra system to do the partial fraction decomposition of this monstrosity. So here was the Laplace transform of y expressed as a combination of various rational functions. We're going to use a computer algebra system to do the partial fraction decomposition. And here it is. So this is a lot simpler to look at, but it's still going to take a bit of work. So the Laplace transform of y is 4 different rational things, each of which on their own is not so bad, but this is exactly what a computer algebra system spit out for me. The first two terms, however, are going to take some manipulation. So here was the Laplace transform of y, as given to us by our computer algebra system once we do partial fraction decomposition. Now, tables of Laplace transforms will typically include this. The Laplace transform of e to the at is 1 over s minus a, and also the Laplace transform of t to the n e to the at is n factorial over s minus a to the n plus 1. Notice that this second one is actually just a shift theorem version of the Laplace transform of just t to the n. This is the Laplace transform of t to the n shifted by a. So now we need to take an inverse Laplace transform of this entire expression. The first term, negative 47s plus 56 over 32 times s minus 2 squared, we're going to attack that one on its own first. We're actually going to represent it in the following way. Having factored a negative sign out, this numerator of 47s plus 56, I'm actually going to call 47s minus 94 plus 150. Now, why on earth would I write that? Well, this numerator, you can factor a 47 out, leaving behind an s minus 2, which you can then cancel 1 power from the denominator. So this first term is actually just equal to this right here. So we've now taken the first term and written it in a slightly simpler way, because now I can take an inverse Laplace transform quite directly. An inverse Laplace transform of what I started with, well, this term here, factor out the minus 47 over 32, and what's left behind is just 1 over s minus 2. Inverse Laplace transform, e to the 2t. Here, once you factor out the minus 150 over 32, what's left is 1 over s minus 2 squared. Inverse Laplace transform of that is t e to the 2t. So we've taken an inverse Laplace transform of the first term produced in our partial fraction decomposition. Okay, we needed to deal with all 4 of these terms, and we've done the first one. So now we're going to move on to the second term, and we're going to employ basically the same trick. That numerator of 1403s plus 2896, noticing we'd like to cancel out an s plus 2, I say, okay, let's call it 1403s plus 2806, and what's left over is I need an extra 90. So now this first term, I can cancel an s plus 2 out from that denominator, leaving behind 1403 over 2400 times 1 over s plus 2, and then I'm going to have 3 over 80 times 1 over s plus 2 squared. So having written the second term in a slightly simpler way, now we'll take an inverse Laplace transform. Okay, so the inverse Laplace transform of this is just 1403 over 2400 e to the minus 2t plus 3/80ths t e to the minus 2t. So let's just remember we had found that the Laplace transform of y was given by these 4 terms, and we found an inverse Laplace transform of the first 2. Thankfully, the third and fourth terms are easier to deal with. Specifically, an inverse Laplace transform of 161 over 50 times s minus 3 is just 161 over 50 e to the 3t, and an inverse Laplace transform of 1 over 6 times s minus 1 is 1 over 6 times e to the t. Okay, so we had stated some time ago the Laplace transform of y is given by these 4 rational terms added together, and we've now found inverse Laplace transforms for each of them. So we can take all of that and put it together to finally state that y is given by, here were 2 terms given by inverse Laplace transform of this. These 2 terms were the inverse Laplace transform of this second bit here, and here had inverse Laplace transform that, and this term had inverse Laplace transform here. So we've completed the problem. We have our solution. Now there's something interesting to point out here. Notice that in our solution, we have terms of the form e to the minus 2t. Up here, we have e to the minus 2t as well. In other words, this portion of our forcing function was actually part of the solution space to the complementary homogeneous equation. If we were doing the method of undetermined coefficients, that would be a very important thing to have known in advance. But using the Laplace transform really didn't need to know that. The fact that e to the minus 2x solves the complementary equation, it never really affected how taking Laplace transforms works. So in summary, what have we discussed? Formulas for Laplace transforms of higher derivative are not terribly complicated, and they're fairly quick to use. So the Laplace transform remains a very useful way to solve higher order differential equations. Now, for practical reasons, we are still restricting ourselves to constant coefficients. And the partial fraction decomposition begins to have lots and lots of terms involved, so it's impractical to do by hand.